now let us look at some examples of how we can model real-life scenarios with systems of differential equations. Right? So first, here is a scenario. So imagine 3 tanks, right? So with volumes, tank 1 is 300 liters, tank 2 is 80 liters, and tank 3 is 100 liters, right? And then the water with sugar, there is sugar, is flowing in the first tank, and then from the outside, and then is draining from the second tank to the outside. And at the same time, there are some pipes between tanks, so that there is water flow from tank 1 to tank 2. There is water flow from tank 2 to tank 3, and from tank 3 to tank 2, and at the same time there is a flow in from tank 2. All right. So now what we are going to model is the amount of sugar in each tank, right? So suppose that in tank 1, x1 is as a function of t is the mass of sugar in the first tank, right? So x2 of t is the mass of sugar in the second tank, and x3 of t is the mass of sugar in the third tank. So then in all the 3 tanks, right? So the rate of change of the mass of sugar, it adds from 2 terms, right? So the rate in is a positive term, so the inflow of sugar, and the rate out is negative term, so is the outflow of sugar. Well, and in any case, the rate of change of the sugar in inflow or in the outflow is going to be concentration times the flow itself, right? So you can imagine that the rate in and the rate out is going to be measured in grams per minute. Concentration is going to be measured in grams per liter, and flow is measured in liters per minute. So when you multiply concentration times flow, liters are cancelled, and the remaining part is just grams per minute. Well, then the amount of sugar in the first tank is what? So that's the rate of change of the sugar in the first tank. Right? So this is coming in from outside. This is given to us 30 times 10. So it's here, right? So 30 is the concentration, and 10 liters per minute is the flow. So it's 30 times 10. Then another source is from tank 3. So in tank 3, notice that this is the flow. So in tank 3, from tank 3, the flow is 2 liters per minute, and the amount of sugar in that flow is going to be sorry, the concentration of sugar is x3 divided by 100, because x3 is the total amount of sugar in tank 3, and 100 is the total volume of tank 3, right? Well, and then the outflow is this, because the outflow is proportional to the well, 12 here is the 12 liters per minute is the outflow from tank 1. I think it goes to tank 2. Yeah. Yeah, and the concentration of sugar in tank 1 is x1 over 300. Well, and then by doing the same thing, we can deduce the equation for x2 and equation for x3. So basically, what we have is a system of differential equations. So we have 3 unknowns, x1, x2, and x3, and one independent variable. And then we can write the system in the matrix form like this. Or notice that the right-hand side of the system is just linear equations on x1, x2, and x3. So it means that we can rewrite it like this. So it is a matrix times x1, x2, x3 plus this constant vector 300, 150, and 0. Okay. So basically that's it. So this is how we modeled the flow of liquids with sugar between 3 tanks. So here is another example, kind of more serious. so we are going to write a system of ordinary differential equations that models the motion of, well, of Earth, or generally speaking of any planet around a star. Right? So we are going to use the Newton's law of universal gravitation. So, and according to that law, the force of the gravitational force is inversely proportional to the square of the distance and is proportional to the masses of the two objects. Well, in our case, we are going to simplify everything. So we are going to assume that the sun is just stays put at the origin, okay, and Earth is orbiting the sun. So we are not going to model the fact that the sun is also affected by gravity, well, by the different planets' gravity, and it's not probably exactly still, but it rather does its own motion. And anyway, right? So we're going to simplify it. So another thing is that we're going to, although it seems kind of intuitively clear that the Earth's trajectory lies within a plane, right? So I mean, of course, the whole thing is in the 3D space, but the actual trajectory is within a certain plane. So we're going to assume that we're going to describe it by just two variables, x and y. Okay. So then acceleration, which is the second derivative of the position, according to Newton's law, is gm over r squared. So here, suppose that x and y is the position of the Earth by time t. So it's not just x and y, but it's rather x of t and y of t. Then we know that r squared equals x squared plus y squared, right? So then the acceleration is actually a vector quantity. So what Newton's law of gravitation tells us is that the norm of the acceleration vector, the length of the acceleration vector, is gm over r squared, right? So it's a scalar quantity, right? So this is what. So if the vector itself is a vector, so then the acceleration scalar is the norm of the vector. Okay. Well, but what is the acceleration vector itself? So acceleration vector itself is going to be directed towards the sun. All right. So let me write it here. This is the vector x, y. Then the vector exactly opposite to it is x, y. But then the unit vector that points in the same direction is x, y divided by its own norm, and its own norm is the square root of the sum of squares of the variables, right? So in other words, this thing here is the unit vector that points from the Earth to the sun. So sorry, this is a unit vector that points from the sun to the Earth. So minus this thing is the vector that points from the Earth to the sun, and then we need to multiply it by a, which is the length of the acceleration vector, and then by putting it together we get these two equations, right? So in other words, the motion of the Earth around the sun is described by a system of two second-order differential equations. But it doesn't stop here. We can actually go further, and we can transform this to a system of first-order equations. So by doing the following thing, we just introduce new variables, right? So u is going to be x prime and v is going to be y prime, and then here is the new system that we are going to get, right? So because if u is x prime, then it means that x double prime is actually u prime, and if v is y prime, then it means that v prime is y double prime. So we're going to replace x prime with u, so x double prime with u prime, and y double prime with v prime here. And so the reason is to change our system of second-order equations to a system of first-order equations.